Hey students, this is a lecture on section 2.3 from our elementary statistics book. And the title of this section is Graphs that Enlighten and Graphs that Deceive. So just in case you don't know, the word enlighten means that the graph tells us something or helps us understand the data and the distribution of the data better. And then most people probably know that the word deceive means that there are certain graphs that can mislead us to believe things about the data that aren't true. This is a fun section with lots of different types of graphs, and we're going to go through all of them. So, what are we going to be learning about first? Well, we're going to introduce graphs that foster understanding of the data. So in other words, understanding of the data is the same as saying graphs that enlighten. That's supposed to say graphs, not graph. Okay, and then the graphs in this section that enlighten are dot plots, stem plots, time series graphs, bar graphs, Pareto charts, pie charts, and frequency polygons. Keep in mind, I say that these are graphs that enlighten because they generally help us understand the shape of the data's distribution, and they help us understand what's really going on by looking at a picture. That being said, there are also graphs that deceive or lie to us, and we're going to be learning about a couple of those. So in the second part of this section, we're going to learn about graphs that deceive because they create impressions about data that are somehow misleading or wrong. Okay, and then the two types of deceptive graphs, or graphs that lie to us, covered in this section are non-zero vertical axis, so we'll see an example of that, and then also pictographs. A lot of people don't realize that pictographs are actually a type of graph that tends to over-exaggerate a change in the data. Okay, so we'll see that at the end. All right, but let's start with these graphs that enlighten us or that are good, a good way of presenting the data. And they enlighten us because they show us the data in a way that helps us understand the shape or distribution of the data. Okay, starting with dot plots. So this right here is a dot plot, and I think we can all see why it's called a dot plot. It has a bunch of little dots. And a dot plot is a graph of quantitative data. Remember that the word quantitative is going to be numbers. So quantitative data means numbers that measure or count something. Okay, so roughly speaking, numbers, but they actually have to be numbers with mathematical meaning. But we've talked about this before. It's in chapter 1 of my lectures. Okay, so in a dot plot, each data value is plotted as a point or a dot above a horizontal scale of values. Dots representing equal values are stacked. Okay, so if we look at this dot plot that we have here, we can see that there's a dot right at 40, and then also a dot just to the right of 40. So obviously the dot at 40 is very likely going to just be a pulse rate. So because here the data represents pulse rates of males, that's going to most likely be a pulse rate of around 40, and then this next one is probably a pulse rate of around 42. So each of those dots represent individual data values in the study. So then when we go to 50 here, we can see that there are two dots, which means that two of the males in this study had a pulse rate that was about 50. And then just to the right of 50, we see 1, 2, 3, 4, 5 dots. So that means actually 5 of the people in this study had a pulse rate that was about 52. And how do I get 52? Well, I can see that going from 50 to 60, there are a total of 1, 2, 3, 4, 5 columns before I get to 60, which means that they're counting in twos. So this is going to be 50, 52, 54, 56, 58, and then we're at 60. So as you can see, a dot plot is very helpful. That's why they call it a graph that enlightens, because it helps us understand the shape of the data. So very clearly in this picture, we can see that these values at 40, around 40, and then also these couple of values that are past 100, these are what we would call outliers. So in a previous section, I introduced outliers. Outliers are data values that are far away from all the others. So I would say these two right here and these two over here are data values that are outliers because they seem kind of out of place. They're far away from all the other data values. So most of the data values are between 50 and what is that? 96. Okay, so between 50 and 96. So these ones that are past 100 or below 50 are considered outliers, whereas all of these other data values are kind of clumped together. And then also notice we can see the shape of the data. This one almost has a normal distribution shape, but the thing is it goes up and down all over the place. So I wouldn't say that it's a normal distribution. I mean, it's much more complicated than that. But certainly looking at the picture, we can see what's going on. We can see that the graph has these little peaks and then valleys. So the graph sort of goes up and down, but we can also see the maximum is right here. The highest point of the graph is right there. And roughly speaking, we can see that the center of the graph is here around 70 without even calculating where the average or the median is. We can just see that the middle of the graph is somewhere around here. Okay, so dot plots are great. And so let's talk about a little bit more about dot plots before we move on the next slide. So we've already seen what a dot plot looks like, but in our book, they say that the features or the good things about a dot plot are going to be, first of all, as we saw on the previous slide, it displays the shape of the distribution of the data. It displays it very well. It organizes the data in such a way that we can really see what's going on with our data. And then another feature, another good thing about a dot plot, it is usually possible to recreate the original list of data values. Now, they say usually. I'm going to say usually. I'm going to leave it at usually because as we saw on the dot plot that's actually on the previous slide, the issue is, for example, in that one, they're counting in twos. So someone might have a heart rate of 51, but how would we know if that person had a heart rate of 51 by looking at this? Like, these two are supposedly 50, and then these 5 here are supposedly 52, but then I'm just wondering, if someone had a heart rate of 51, would they round it up or round it down? So as you can see, you can figure out roughly what the original data values were, but if they do things like this where they're counting in twos or counting in fives or whatever, you might not be able to get the exact original data values. So it's usually possible to recreate the original list of data values, at least roughly speaking. Okay, but one way to make it so that you can actually figure out the individual data values would just be to instead of counting in 2s on your horizontal axis, you could count in 1s. And then you would get the actual pulse rate as whole numbers. Then you'd be able to tell if someone had a pulse rate of 51 versus a pulse rate of 50 or 52. Whereas here we can't really tell because they must have rounded it either up or rounded it down. Okay, so those are dot plots. Very good graphs. They definitely show us a lot about the data. Okay, next type of graph that enlightens, this is another type of graph that generally fosters understanding of the data, are stem plots. So stem plots or stem and leaf plots, depending on what you're looking at, these two terms mean the same thing. So a stem plot or a stem and leaf plot, what they do is they represent quantitative data. Again, you should remember what quantitative means by now, but just in case you don't, we'd already talked about it on this video. Quantitative just means that it has to represent numbers, that the data have to be numbers that count or measure something. Okay, so anyway, a stem and leaf plot represents quantitative data or numbers by separating each value into two parts. So the first part is the stem. These are the leftmost digits. So for example, if we look at this stem plot down here, we can see that these numbers on the left side are all of the stems. So the first stem is 4, the next stem is 5, 6, 7, 8, 9, 10. Okay, those are called the stems, those numbers on the left. And then on this particular stem and leaf plot, they put sort of a vertical divider here to show you that that's the end of the stems. And then all these numbers on the right, there are a lot more of them, those are called the leaves. Okay? And for the leaves, each of the digits to the right of the stem are considered leaves. So for example, in this first row here, our stem is 4, and then our 2 leaves are 0 and 2. So what does that tell us? Well, if we're just looking at that first stem and those first 2 leaves, each leaf indicates that we have an individual data value there. So the 0 and the 2 translates into, well, the first digit is a 4, and then the next digit is a 0 for the first one, and then a 2 for the second one. So you get 40, so 40, and then 42. So these two pulse rates are 40 and 42. Okay, so, and then down here, for example, at the 9, we would say our stem is 9, that's the number on the left. And really, keep in mind that the stems on this particular stem plot are representing the tens digit, okay, and then the leaves are representing the ones digit. It doesn't always have to be that way, though. You can make stem plots that where the stems are actually representing the hundreds or the thousands or the 10,000s digit, and then the leaves could represent other things. But usually it's going to be this setup. And you can also have stem plots for decimals. But again, for our homework, they're generally going to be set up this way, where the stems are the tens digit, and then the leaves, these numbers on the right, are the ones digit. So anyway, going back to this, if we look at the stem of 9, then we have to the right of it these leaves, which are 0, 2, 4, 6, and 6. So what this represents is each of these leaves tell us that we have a data value there. So the first leaf tells us that we have a data value of 90, the second leaf 92, then 94, and then 96 and 96. So that means there are 2 data values that were 96. So just out of that row for 9, we got pulse rates, which are 90, 92, 94, and then because there were 2 6s there, we got 96 twice. As you can see, just looking at this, we can, hopefully not hurt our neck by looking at it sideways. But if we turn our head sideways carefully, we can kind of see the shape of the data. And another nice thing about it is, even though it has a bunch of numbers, it's still a graph. So you can still see the shape of the graph. And so obviously, with this graph, most of the data values were between a tens digit of 5 and a tens digit of 8. Okay. All right. And another nice thing about it is, because it has these numbers, you're supposed to be able to get the exact data values back. But once again, as we can see here with these pulse rates, they're rounding to the nearest 2 rather than to the nearest 1. So I don't know if that's how they gathered the data, or if they actually had people that had a pulse rate of 61 and then they would round that up to 62. I'm not sure how they ran the study exactly. But as you can see, with this one, we could easily have measured the pulse rates to the nearest ones digit, but they haven't done that on this one. Okay, so what's so great about stem plots? We've already seen it. The features or the good things about a stem plot are it shows the shape of the distribution of the data. It retains the original data values, supposedly. And I honestly feel like it's easier to get the original data values from a stem plot than it was to get from a dot plot. But both of those have that capability. All right, and then the third feature is the sample data are sorted, so they're arranged in order. But really, all three of those features are also features of the dot plot that we saw. But it's just nice to have a different way of displaying the same data. Okay, so that is a stem plot. Cool. Okay, next type of graph. We're going to see a lot of different types of graphs, so I have to keep moving. Otherwise, this video is going to be like 3 hours long or something. Okay, so next type of graph, time series graph. So if you listen to the name of this, it has the word time in it. And surprise, surprise, the horizontal axis is now representing time. In this particular time series graph that we see here, the horizontal axis is representing years, okay? But obviously we can measure time in any unit that represents time. So it could, instead of years, it could be hundreds of years. Or it could be a lot smaller. It could be in weeks or days or months or seconds or minutes or hours, any measurement of time. But what's important is that with a graph of time series data, which are once again quantitative data, so we're looking at numbers, these have to be data that are collected regularly at different points in time. And the reason I say regularly is you don't want to have any missing data here. So you'll notice there's a dot appearing regularly for each point in time. So if we look on the horizontal axis, it's starting at 1985. And so this first dot here tells us that the number of, well, the vertical axis is law enforcement fatalities. The number of law enforcement fatalities in this time series graph was a little bit shy of 180. So they don't have it that well labeled, but we can see there were almost 180 law enforcement fatalities in the year 1985. And of course, it would be helpful if we had more context for this particular graph. But as we can see, the nice thing about this graph is we can see what are called trends in the data. So from 1985 all the way up to 1990, we could see a small increase as we go from left to right in the number of law enforcement fatalities. And then all of a sudden, around 1990, or at least 1989, there was a sudden drop in the number of fatalities. It decreased here, and then it started increasing again to 1995, and so forth. So you can see the graph. You can see that it very easily allows us to see what's going on over time. And of course, that's a useful thing, not just for this particular example. There are all kinds of time series graphs. So for example, people who are interested in investing in stocks or bonds on Wall Street, if you go to a stock market website, or you go actually to Wall Street, the display of the value of a stock will go up and down just like this graph over time. But once again, you could have a graph of the value of a stock as a time series graph, even just for a day, and it may go up and down. For example, Amazon stock has been mostly increasing over the past 10 or 20 years, but then if you have a smaller period of time, it may have some variation, So stocks are another type of time series graph that you'll see in the real world. Okay, so what's so good about a time series graph is primarily just that it reveals information about trends over time. So it's a very special type of graph, but is also a type of graph that enlightens, because it shows us something. It helps us understand what is going on with our data over time. Okay? All right. Next type of graph is a bar graph. Now, make sure you've watched my earlier lectures, in particular the last lecture before this one on section 2.2 from our elementary statistics book, because I did talk about the difference between bar graphs and histograms in 2.2. 2.2 was all about histograms, but I took a good 5 or 10 minutes to do a sketch of a bar graph right next to a sketch of a histogram, and I'm not going to do that again here. So we've already seen the difference, but here I'm just going to mention briefly, just to summarize what we learned in that last lecture. Remember that a bar graph is going to have bars of equal width, just like a histogram, but what's important is that the horizontal axis has to represent categories of categorical data. So categorical or qualitative data means that the data is not numbers that measure or count something. Instead of that, it's actually going to be categories or labels, okay, for our horizontal axis. So that's one of the primary ways you know it's a bar graph and not a histogram. Another thing about bar graphs is the book says the bars may or may not be separated by small gaps. But I say in most bar graphs that are just bar graphs, there usually are gaps. Not 100% of the time, but usually if there are gaps between each bar, that's another sign that it's a bar graph and not a histogram. And remember, with a histogram, all the bars are right next to each other. Okay? But even so, occasionally you'll see a bar graph where they put the bars right next to each other, just like in a histogram. But remember that a histogram has to have quantitative data or the actual numbers, range of numbers for each class for the horizontal axis, as opposed to the categorical data that is represented on your horizontal axis for bar graphs. Okay, so feature of a bar graph. What's good about bar graphs is it shows the relative distribution of categorical data so that it is easier to compare the different categories. Which is nice because all of the graphs we've learned in this section, and then also histograms in 2.2, all of those graphs have only been for quantitative data. Whereas bar graphs are the first type of graph that we've seen in this class that represent categorical or qualitative data. So categories, names, labels, rather than actual numbers. Okay? All right, but I'm not going to draw another bar graph. However, we are going to talk about a special type of bar graph that shows up on your homework, quiz, and exam. This is the most important type of bar graph. I guess you could technically call a histogram a bar graph, but that's a little bit frowned upon. Even though it looks like a bar graph, it's technically called a histogram because it has quantitative data. Well, in this slide, we're learning about Pareto charts. Now, Pareto charts are definitely bar graphs, okay? So they're not histograms. So a Pareto chart is a bar graph for categorical data. Like we just said, bar graphs always represent categorical data, not numbers, with the added stipulation that the bars are arranged in descending order according to the frequencies. Now, vertically speaking, the height of each bar is still going to represent a number, but on the horizontal axis, we're going to see categories. So let me just jump ahead so we can see the picture. So here we have a picture of a Pareto chart, and we're going to talk about this in detail, but notice that this particular Pareto chart is cause of fatal plane crashes in a certain year. They didn't indicate which year this was, but this is out of our book. Anyway, what's important is we know it's a bar graph because the horizontal axis is actually representing categories, not numbers. Pilot error, mechanical, sabotage, weather, and then other. Those are categories, categorical data. Even though the height of each bar is representing a frequency, in other words, the number of fatal plane crashes during that year. I forget which year it was, but this is in our textbook if you want to look it up. Anyway, that is a Pareto chart, and something else that you'll notice about it is that with a Pareto chart, as you go from left to right, each bar has to be smaller than the previous one. So pilot error is the tallest bar, mechanical is the next tallest bar, sabotage is shorter, and then weather is the shortest. And the only exception to that rule, which is called descending order, where you decrease in height as you go from left to right, the only exception to that can be the very last category, which, as we see in this Pareto chart, seems kind of out of place because the reason that this one isn't decreasing is it's sort of separate from all the other categories. So they're calling this last category other, which means they're lumping a bunch of miscellaneous data values all together. So it's still considered a Pareto chart, even if this very last bar seems out of place, because this last bar is sort of a combination of all the other categories, miscellaneous categories, and they've clumped them and added them all together just in this other category. But other than that, other than the other, we can see that we have a decreasing or descending order here. So it's a Pareto chart. Okay, so we've seen it in detail. The bars are arranged in descending order according to frequencies, so the bars decrease in height from left to right. However, an important note, sometimes the rightmost bar can represent a miscellaneous category, such as other, which may not follow the descending order, as we saw in the picture, as we saw in the graph. Okay? What are the features of a Pareto chart? Why do they enlighten us? Well, it shows the relative distribution of categorical data, just like any other bar graph, so that it is easier to compare the different categories. Okay? That's good because it's kind of hard when you just have categories. How are you going to compare everything? Well, because they're in descending order, we can just look at the graph and see right off the bat, if we look at the left side of the graph, we already know that the most common cause of a fatal plane crash is this first bar, which is pilot error. And then as we're reading from left to right, we can easily see the relative importance of each of these categories. So it's actually more helpful than a bar graph where the bars are just in some random order, or if they're in alphabetic order, which doesn't mean anything usually. With a Pareto chart, because the most important category is first, and then it decreases as you go from left to right, that's more helpful than just a regular bar graph. So as I was saying, features of a Pareto chart, it draws attention to the more important categories because they're on the left side. Okay. All right, so that's Pareto charts. Very helpful type of bar graph that shows up on your homework, quiz, and exam. Now, a very common graph that's used all the time in the real world. Our book calls it a pie chart, and there are other names for it. A pie chart is a common graph that depicts categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. Okay, so this is the second type of graph that we're learning about that is actually for categorical data. Now, another name for these are circle graphs. Okay, so pie chart, aka also known as a circle graph. I mean, there are lots of different names for them, but circle graph is the only one that's popping into my mind right now. Our book calls them pie charts. Anyway, a picture's worth 1,000 words, so let's take a look at a pie chart. Obviously, the word pie, P-I-E, kind of tells us that we're expecting something like a pizza pie or, my favorite, chocolate cream pie. Well, I like all types of pie, apple pie, anyway. They're delicious. But we can see that this is sort of like a pie because we have a circle, and then we have the circle divided into slices. And then they have different colors for each slice. And this pie chart would be more useful if they would actually have some sort of percentage, or at least indicate the frequency for each of these slices of the pie. But they haven't done that here. So if they don't provide you with percentages or numbers, you're just stuck like this looking at, well, we can see that pilot error is definitely the biggest slice. That's more than half of the pie. And then the next biggest slice would be mechanical, which looks like it's, a bit less than 1/4 of the graph. And then past mechanical, we've got sabotage, and then weather. And then, of course, other would be all of the other causes of fatal plane crashes, where they've just added them all together and lumped them all into this orange pie slice here. Pumpkin pie is good too, but pumpkin pie isn't my favorite. All right. Although it is pretty good with whipped cream. I feel like I like the whipped cream more than the pumpkin pie. All right, anyway, pie chart or circle graph is very common. It's used a lot. However, it's not considered as useful as a Pareto chart, by our book at least. And I tend to agree with our book here. Pie charts are useful because they do show the distribution of categorical data, and this is a commonly used format, so people are used to seeing them. However, our book does say that pie charts are generally less enlightening or less useful than Pareto charts. You need to know that because one of your homework questions, they actually ask you, they have you construct a pie chart. Well, you don't really have to construct it because it's multiple choice. So you have to choose the correct graph. And then after you choose it, they ask you what's more helpful, a pie chart or a Pareto chart? And the answer is a Pareto chart is considered, at least by the author of our book, to be more useful than a pie chart. So let me write that down because you're going to need that for your homework. So our author of our book considers Pareto chart charts to be better or more enlightening than pie charts. Okay. Pie charts, aka circle graphs or circle charts. I mean, there's all kinds of names for them, but it's a circle and it looks like a pie because it's divided into slices. So the author of our book considers Pareto charts better than, when I say better than, I just mean more enlightening than pie charts. So whether we agree with his opinion or not, we need to choose that when we're doing that particular homework problem that asks us that. So that's why I'm covering it here in our lecture. Okay? All right. So, of course, even if you don't agree with the author, I tend to agree with him that looking at a circle graph or a pie chart is less useful than looking at a Pareto chart, because with a Pareto chart, everything's sort of organized from left to right, whereas with the pie chart, we can see that things are more difficult to order. And it's just, it's really a matter of opinion, but the Pareto chart is considered usually superior. All right, so let's go ahead and, believe it or not, we're going to learn about even more graphs in this section. It's a big section. But it's kind of a fun section because we actually get to see all different types of graphs. And when you're doing your homework, rather than having to construct any of these graphs by hand, you'll literally just have to choose the correct graph from a list of graphs. So it'll be multiple choice for the graphs. But they will also ask you to interpret the graphs. Okay, so next type of graph is called a frequency polygon. Now, if you've taken a class before that covers geometry, you may have seen the word polygon before. Polygon basically just means a figure such as a triangle, a square, a rectangle, and a polygon has a certain number of sides, but it's not a circle, okay? It has, each side connects to another side via a vertex, okay? So a frequency polygon is kind of the same idea as a polygon from geometry, but not exactly, because we're not seeing triangles and squares. But that being said, here's an example of a frequency polygon. This is actually taken from the daily commute times that we constructed our histogram from and our frequency table from in 2.1 and 2.2. So why do you think they call it a polygon? Well, you still have sides, and then you have dots, which represent vertexes or vertices. So as you can see, if you want to see it as a type of polygon, really the name kind of comes from the fact that, Well, there's a triangle. Or if I join these two, you have a quadrilateral. Okay, so that's sort of where the name came from, because it has sides and vertexes, even though it's technically not necessarily the polygon that you learn from geometry. It kind of has the same idea. So it's not a smooth graph, but you can construct this graph, and it's another way of looking at a frequency table that's not a histogram, but it's actually displaying the same data that we use to display in a histogram. So what's good about this is it's another way of looking at a frequency table that's not a histogram. Okay, it's just nice to have a different picture displaying the same data. Okay, so a frequency polygon is a graph that uses line segments connected to points located directly above class midpoint values. So like here, the -8, the 7, the 22, the 37, and so forth, those are supposed to represent class midpoint values. And of course, you can't have a commute time of -8 minutes. So it's a little bit strange the way they have this particular frequency polygon constructed, but it's still useful because it's another way of showing the data that's not a histogram. Okay, so a frequency polygon is very similar to a histogram, but a frequency polygon uses line segments instead of bars. Okay. And then also, just the same way we had a frequency table and a relative frequency table, or a histogram and a relative frequency histogram, there's also a regular frequency polygon, and then there's the relative frequency polygon. So you can construct those as well. And the only difference, just like with the histograms, is that a relative frequency polygon is going to use relative frequencies, which are usually represented as percentages, but also more rarely as decimals or fractions, aka proportions, for the vertical scale. So if we look at this one here, this one is a frequency polygon because we can see that the vertical axis represents frequency. And as you can see here, just like with a histogram, you can look at each dot here, and that will tell us the frequency for that class. So if I look at this first dot, that looks like it's 6 is the frequency of the first class, and the class midpoint for that first class is 7. And this is actually the same exact data that we used in 2.1 when we were constructing our frequency table from scratch using the commute times from LA that are taken out of our book. Okay, so then what would a relative frequency polygon look like? All you would do is, instead of this vertical axis being frequency, the vertical axis would be relative frequency. Okay, and if it's relative frequency, then usually the way they would display it would be percentages instead of the actual frequencies on your vertical axis. But keep in mind that just like with a histogram, a relative frequency polygon will have the exact shape that the frequency polygon does. Even though the vertical axis is now percentages, it doesn't distort the shape. Okay, so here, picture's worth 1,000 words. Relative frequency polygon. We can see that the vertical axis, even though they didn't label it, they have percentages here, which means each of these dots represent relative frequencies. And they've multiplied them times 100% to turn them into percentages. And one nice use of relative frequency polygons is, such as in this graph, is where you actually have two data sets and you can display them on the same graph. So that's more difficult to do if you have a histogram. This wouldn't really work if you had a histogram. But for relative frequency polygons, because we don't have bars overlapping like with histograms, if you put two histograms on top of each other, it can be confusing. Here, with the relative frequency polygon, we can actually see the shape of both the Los Angeles commute times and then the Boise, Idaho commute times from the book. And for example, we can see that here in Boise, a commute time with a class midpoint of 22 minutes is more common. It's almost 50% of the commuters in Boise had a class midpoint of 22 minutes, whereas only about a little bit over 30% of the commuters in Los Angeles had that same commute time, or that range of commute times. So once again, just remember that these numbers on the horizontal axis are class midpoints, which we already went over how to calculate in section 2.1, part 2. Okay. But this really helps. This graph here with the two separate data sets really shows one of the great things about a relative frequency polygon, which is just in comparing data sets. Okay. So far we've talked about graphs that enlighten. So just as a summary, let me go back to our key concept thing at the beginning here. So we already talked about this at the beginning of the lecture. So we've learned about all the graphs that enlighten, or that are supposed to enlighten. Dot plots, stem plots, time series graphs, bar graphs, Pareto charts, pie charts, and frequency polygons. So as long as we display these graphs correctly, those are all considered graphs that foster understanding, or graphs that enlighten us, help us understand what's going on. Now, what about graphs that lie to us? Well, technically, any of these graphs that enlighten could lie to us if we distort them in some way. But probably the most important way that a lot of people will lie using a graph is to have a non-zero vertical axis. Okay? And this can be in a number of different types of graphs. But for our example, we're just going to look at a bar graph, because that's probably the easiest way to see an example of this. So when I say non-zero vertical axis, I just mean, for example, in a bar graph, it would be where we start at some number on our vertical axis. We start at some number besides 0. So if you look at this bar graph on the left, and then the bar graph on the right, believe it or not, these two bar graphs are supposed to be representing the exact same data set. Okay? So what gives? Why do they look so different? I mean, on the graph on the left, if you just look at it and you don't read the numbers, on the graph on the left, it looks like the placebo is basically 0, just looking at it. And then OxyContin is like maybe 10 or 15 times as tall as that. Whereas for this graph on the right, it's not nearly as pronounced. So looking at this graph on the right, without looking at the numbers, the graph on the right maybe looks like placebo is, maybe half the height of OxyContin. So 10 times the height versus half the height. But like I said, these two graphs here, the graph on the left and the graph on the right, these are representing the same data values. So as you can see, something's wrong here. And what's wrong is with the graph on the left. So this graph on the left has a non-zero vertical axis. So if you'll notice, if you can read this, this graph starts at 10%. Okay? So that graph starts at 10%. So if it starts at, there's not really enough room to write here, so I'm just going to have to write a bit smaller. So starts at 10%. Okay, that is the smallest number in the vertical axis. Whereas this graph over here, which is representing the same data, if you look on the left side on the vertical axis, this graph starts where it's supposed to start, which is at 0%. Starts at 0%. So the graph on the left is an example of a graph that deceives. It's deceptive because it's lying to us. So the graph on the left, by starting at a number besides 0, a non-zero vertical axis, it makes us think that OxyContin is causing about 10 times the nausea percentage of the placebo. Just looking at the heights of the bars without reading the numbers, which is what a lot of people do. A lot of people will just look at the heights of the bars because they like the picture, and then they won't really pay much attention to the numbers, and most people wouldn't notice that this graph doesn't start at 0, and so it's lying to us in a way. This graph on the right is not deceptive. This graph on the right is a bar graph that enlightens. So this is a good graph. Because it starts at 0, we can actually see that the heights of these bars do represent their relative importance compared to one and the other. So the graph on the left deceives, which is not a good thing. Again, I got to write smaller. I swear I'll eventually get used to this new recording setup. Okay, so this deceives. Okay. It deceives because it starts at a number besides 0, which distorts the relative importance. Whereas this one on the right, because it starts at 0 on the vertical axis, we would say that this is a graph that enlightens. So I'm going to write that up here above this one. Okay, so this is a graph that enlightens. Okay, so here at the bottom, our book says, always examine a graph carefully to see whether a vertical axis begins at some point other than 0 so that differences are exaggerated. So you might be wondering, well, why do people even make graphs like the graph on the left if it's just lying to people? Well, this just comes back to the idea of bias, where if the person presenting the data or the group of people presenting the data have a special interest in presenting the data in a way that's biased, that's lying to you, they will do it. Like a company, I think I've given this example before, but if a cigarette company is funding a study, then they would want you to think that cigarettes are cool, or cigarettes aren't as bad for you as they really are for you, that kind of thing. Or like here, this is saying that for OxyContin, this graph on the left and this graph on the right, this bar on the left and the bar on the right, maybe for this first graph, we might want to use this one even though it's lying to us if we wanted to make OxyContin seem like it caused a lot of nausea. Like maybe the company that doesn't like OxyContin and wants you to use their drug would use this graph on the left because they have a special interest in making the data look like OxyContin is going to make everyone have nausea. But you shouldn't do that. You don't want your your graph to be misleading. You don't want your graph to lie to people. So you want to use graphs that enlighten so that people know the truth, not a distorted version of the truth. Okay? So, what we just learned about is a non-zero vertical axis, which is a common deceptive graph that lies to us, and it involves using a vertical scale that starts at some value greater than 0 to exaggerate differences between groups. Okay, so that's what we just saw. So this is actually the most common type of deception that people use all the time. Okay, another type of graph, the other type of graph that we're going to learn about that distorts the data that we're presenting is called a pictograph. Now you might be thinking, well, I've seen pictographs before. They use them in magazines. They use them in all sorts of this and that. Well, just because you see it on the internet or you see it in a magazine or in a newspaper doesn't mean that it's not biased, okay? So pictographs are inherently biased. They're misleading. They lie to you. They deceive you. Pictographs, I'm sure you've seen one before. If not, we're going to take a look at one right now. The reason they're deceiving is they're usually representing data that are one-dimensional in nature, such as budget amounts or anything that's one-dimensional. But we're depicting those one-dimensional numbers with two-dimensional objects, such as dollar bills, or three-dimensional objects, such as stacks of coins, homes, or barrels. So you might be thinking, well, what's wrong with that? I don't see anything wrong with that. Well, the problem is just the way area and volume work in the real world. So when you're using a pictograph, artists can create false impressions that grossly distort differences by using principles of basic geometry. So the issue really here with pictographs is because of the way area and volume work, they will greatly exaggerate differences between data values. Okay, so in particular, if you double the side of a square, its area doesn't double. It actually increases by a factor of 4. So, so that's interesting. So if you have a pictograph such as this one here, each of these pictures, even though it looks like a 3D picture, these are 2D pictures, two-dimensional. If you look at the area of this first picture, imagine it as a square. We draw a square around it. I'm not going to draw a square around it, but just imagine there's a square around this first telephone and a square around the second telephone. Just looking at the pictures, I want to say that this picture on the left might be like, 1/8, 1/9, or maybe even 1/10 the size of the picture on the right. Now, what I'm actually referring to when I say size is I'm just looking at the picture and I'm actually, in my mind, I'm kind of imagining the area when I'm talking about size. But the thing is, this is exaggerating the difference between these 2 years. So in the pictures, I want to say the phone on the right is about, 8, 9, or 10 times the size of the phone on the left. But if we look at the actual numbers here, 151 million and 534 million, that's only about 3.5 times, 3 to 4 times going from 151 million to 534 million. the actual numbers are only 3 or 4 times apart, whereas the area of the figure on the right is closer to 10 times. So as you can see, if we go back to this slide, if you're doubling the side of a square, its area doesn't double, it increases by a factor of 4. So I would say with these numbers, just looking at the numbers tells you what's really going on, but the pictographs make us think that there's a lot more of an increase, not an increase of 3.5 or 4 times, but more like an increase of maybe 8 times, 9 times, or even 10 times the area. So it's basically just using geometry to lie to us. And when you're doing your homework, you're also going to see a pictograph that involves volume. And with volume, the distortion is even worse. Okay, so with these telephones here, these are exploiting the fact that an area of a square is actually, when you increase the area of a square, if you increase the side of a square, the area goes up by a lot more. Well, when you double or increase in some way the side of a cube, its volume doesn't merely double, it increases by a factor of 8. So on your homework, you will see something like 2 figures that are pictographs, but they're actually representing volume, and then they will exaggerate the difference between the 2 numbers even more. Because instead of multiplying by 2 to get the volume in the new figure, you're actually going to be multiplying by 8. Okay. So even if you don't like geometry and you don't care about geometry, what's important is that you cannot trust pictographs because they lie to you using the principles of area and volume, and they distort the data. Okay? All right, so concluding thoughts to finish up this lecture. In addition to the graphs we have discussed in this section, there are many more other useful graphs, some of which have not yet been created. The world needs more people who can create original graphs that enlighten us about the nature of data, not graphs that deceive us or lie to us. Okay. This is straight out of our book, but I found it helpful. I think it's some good general guidelines. So in the visual display of quantitative information, the author Edward Tufte offers these principles. So for small data sets of 20 values or fewer, use a table instead of a graph. So that can be useful if you don't have a lot of data values to just make something like a frequency table. And then sometimes a histogram could be helpful. But here they're saying that it might be better to just use a table rather than a graph if you don't have that many data values. So that's a good general guideline. The next thing that this author recommends is that a graph of data should make us focus on the true nature of the data, not on other elements such as eye-catching but distracting design features. So we haven't really seen distracting design features, but pictographs are sort of like that. So they sort of mislead us. Because they have pictures, people just look at the pictures, and many people won't read the numbers because they can't understand these numbers as well as they can just looking at the pictures. So they get lied to and they believe it. So that's sort of an example of a distracting design feature, to mislead or deceive people. Okay, another recommendation of that author is do not distort the data. Construct a graph to reveal the true nature of the data. In particular, here we saw how you could grossly distort the data by starting, for your vertical axis, starting at some number other than 0. Gave us a very distorted graph whereas the truth was this graph on the right. This is what it's supposed to look like. Okay. Right, and then his last recommendation is almost all of the ink in a graph should be used for the data, not for other design elements. Okay, now we haven't seen these, but if you look at a lot of things on the internet, they'll have lots of design elements to make the graph look cooler, but those design elements can distract people from actually understanding the shape of the distribution. So that kind of stuff should be avoided, even though newspapers, magazines, and everything on the internet wants to sell whatever it is, their newspaper story, their magazine, or they want you to click on their stuff to go on their website if it's online. But that kind of stuff you can't trust. So you want your data to be not biased, but you also want the way you display your data in graphs to not mislead or deceive people. Okay, so that is the end of the slides from section 2.3. So that was quite long, longer than an hour, but at least it didn't end up taking me 3 hours like I was worried. So thank you for watching, and I hope this prepares you well for your homework, quiz, and exam. I think it will. All right, see you next time.